Hello IB. Today we're looking at 12H, which is just a follow-on from 12G where we introduce vectors in 3D space. 12H just looks at all the operations that we have done already with 2D vectors, and they're all exactly the same here, but we're just adding that extra dimension. So if we've got our two vectors in 3D space, we've got vector A, A1, A2, A3 for the X, Y, Z directions or coordinates. And this is the vector notation, not the coordinates for the point. If we want to add two vectors, then we're just going to be adding the X components, the Y components, and the Z components. Or if we're subtracting them, we're subtracting those components. If we want to multiply by some scalar, and we know that that scalar can be any sort of real number. It doesn't matter whether it's positive or negative, fraction, decimal, irrational, or anything. Then we just multiply each of the components by that scalar. The rules for adding vectors are the same as what we looked at beforehand. It doesn't matter what order we add those, the commutative property, then we can do that. It doesn't matter whether we add A and B first or B and C first. If we add the zero vector, it makes no difference. We just end up with A. If we add a vector A and its opposite, minus A, then we get a net result of zero, a zero vector. If we want the magnitude of our vector that's been multiplied by a scalar, then we can effectively get the magnitude of the scalar times the magnitude of the vector. So it's just about notation here. We're saying what's the actual length of that vector. The modulus of k is where we're using the absolute value. So if our value is, say, minus 2, then we're taking 2. This notation here is talking about the length of A. So here's the same notation, but with different meanings because k is a scalar and A is a vector. So here those straight lines mean the length of that vector. Here the absolute value signs means the modulus of k. So if we've got our example, A is equal to some vector 1, 2, minus 3, then our vector, when we multiply by minus 2, is simply just going to be minus 2 times each of those components. So we'll have minus 2, minus 4, and plus 6. If we're wanting the length of that new vector, minus 2a, vector A, we want the length of that, then we can take the modulus of minus 2, which means take the absolute value of that, and then multiply. We don't have to put that multiply symbol between them. Multiplied by the vector A, all right, by the length of that vector. So the absolute value of minus 2 is 2. And then we're going to multiply by the length of our vector A, which is 1 squared plus 2 squared plus minus 3 squared. When you multiply that out, we get 2 square root of 9 plus 1, 14. So 2 root 14 is the length of that vector. Other algebraic operations, in other words, involving some unknown vector. If we're trying to find a vector x, when added to A makes vector B, then we can just subtract A from both sides. We can do our normal algebra with our vectors, subtract A from both sides, and then we end up with x is equal to B minus A. If we know that k is equal to some vector, k times some vector equals a, then our vector x is equal to 1 over k times a, where as long as k is not equal to 0. Also, just notation, we don't write a division like this. We always write it as 1 over k, so our scalar is 1 on k multiplied, so we don't write a division that way. Here, in this example, we've got our vector A, which is, let's say, it can be defined as OA from the origin, vector B is OB from the origin. Then AB is equal to B minus A. So if remember, if we want to go from A to B, oh, nice straight line, then to get from there to there, it's the same as doing the opposite of this. So we want minus A plus B, and that gets the same result. So we want B minus A. Remember, the order of those being subtracted doesn't, well, the order of them being sort of added together doesn't matter. So we're adding B plus minus A. So that's that one. If we wanted to do going from B to A, so that means we want to go that direction, then that would be the same as starting with the opposite of B. So we want to go minus B, and then add A. We can tuck it in here. All right. So we want to go minus B plus A, which is the same as, so that's the same as minus B plus A. And we've just swapped the order. So let's just try this. In this example here, we've got a vector A and a vector B. If we want to find X, then we want to do our algebra with this. So pause the video and then come back and have a look and see how you go. So do your vector, just a normal algebraic operation to make X the subject, and then substituting your two vectors. So pause and have a look. All right, so hopefully you'll be able to add A to both sides. Next step we then want to do is we can substitute it at this point, or you could have made a third and put brackets around it. So substituting your two vectors, 2b, which is 2 minus 2, 1, plus minus 1, 2, 3 for vector A. Put those together. So we want 2 times 2, which is 4, plus minus 1 makes 3. So this is our vector, 3x is equal to that. Then the last stage is to divide both sides by 3. So 3 divided by 3 is 1, minus 2 over 3 is minus 2/3, and 5 over 3 for the y component. In this next example, what we want to do here is work out the coordinates of C. So if we're trying to find C, then can I encourage you always just to set up your equation to start with. So OC is equal to OB plus BC. Remember, we always want to make sure we set up our vector equation with those two the same. Once we've done that, we go, well, we don't know BC, but because these are the same length, then we can say that AB is the same as BC. So we can make that statement, which means we can now substitute in our coordinates for B, OB, then AB is our translation vector. So how do we get from A to B? Remember, you want to do the B coordinate minus the A. When you're doing that, so it's minus 1 minus minus 2, minus 2 minus minus 5, and 2 minus 3. So that gives us our translation vector of minus 1 plus 2 makes plus 1, minus 2 plus 5 is 3, 2 minus 3 is minus 1. So that's our vector that takes us from A to B, and we want to do the same for B to C. So we can now add that vector to our initial point of B, and we come up with our coordinates of OC. In other words, the coordinates of C is 0, 1, 1. If it wants coordinates, write it as a point. Stop now and see if you can write the correct vector equation to get the coordinates of D, and substitute in what you need to come out with the coordinates of D, and then we'll have a look at that one in class. The other one we want to have a look at, and we'll finish this one in class, is getting our vector methods to find the fourth coordinate of our parallelogram. So again, we're back into 2 dimensions with this. We don't need to plot it up on the coordinate plane. It doesn't matter what it really looks like. We can work with this. So we want to get a transformation vector. If we're trying to find this coordinate, then we see we can either get that from starting at A and find this vector, or we could say, let's start with C and then add that vector on. So it doesn't matter which way you work. If we go with, let's say we want to do the A, then going to D, then we want to write the vector equation we want to get the coordinates of D is OD will equal OA, start with A, and then add on AD. But we don't know AD, but we do know that AD is the same as BC. And that's the direction we want, from B to C, because they're parallel. So therefore we can now write the statement OA plus BC, that's equal to our OD. So just get in the habit of writing that correct statement and doing your substitution. So have a go at doing that one, and we'll finish that up in class. So a nice, short, easy one today. Make sure you make good notes, and we'll see you in class. Thanks for listening.